In section 2.4, we established the protocols that we'll be using for writing chemical formulas. So chemical formulas can be depicted in a variety of ways. Perhaps the most common way of indicating a molecular formula is with, what we call the molecular formula. So what the molecular formula does is indicates the number and type of atoms found in one molecule. And it's effectively what we do is we write out the symbol for each atom. And if there is more than one of that atom, then we indicate how many of that atom there is by a subscript with the correct number there following the atom's symbol. If there's only one of the atom, it doesn't get a subscript. A structural formula is a little bit different. A structural formula tries to show you how the atoms are arranged in three-dimensional space, how the atoms are connected to one another. So the structural formula for CH4 indicates that there is a central carbon atom, and then attached to that are 4 hydrogen atoms, as opposed to, say, something more like that. That is not how the atoms are organized in the CH4 molecule. Chemists will often use what we call models to illustrate how atoms are arranged either in a molecule or a crystal with respect to 3D space. Common models include ball and stick models, where atoms are shown as spheres and bonds are shown as sticks, or space-filling models where molecules are illustrated using overlapping spheres. It's important to recognize that if a compound is a crystal, then there's no molecules present and we can't give a molecular formula. A crystal is a repeating pattern of ions or atoms that extends almost indefinitely in all 3 dimensions, so talking about molecules doesn't really make sense. So for that reason, we don't give a molecular formula for a crystalline compound. So that's a bit of a difficulty, and we're going to have to work to get around that. We can define for a particular compound what is referred to as the empirical formula of the compound, and that is the smallest whole number ratio of the elements present in a compound. This may or may not be the same as the molecular formula. Sometimes it is smaller than the molecular formula. So for example, hydrogen peroxide has the molecular formula H2O2. However, its simplest ratio of atom types, its empirical formula, would be just HO. Water has empirical and molecular formula H2O. The molecular formula of a molecular compound is always a whole number multiple of the empirical formula. So here are a series of examples. We have these compounds here: dinitrogen tetrafluoride, hydrogen peroxide, methane, and benzene. The empirical formula of dinitrogen tetrafluoride is NF2, but its molecular formula is 2 times its empirical formula and is N2F4. Hydrogen peroxide, as we saw previously, has the empirical formula HO, but its molecular formula is 2 times the empirical formula and is H2O2. The empirical formula of methane is CH4, and its molecular formula is also CH4. So simply 1 times the empirical formula. The empirical formula of benzene is CH, but its molecular formula is 6 times that, which is C6H6. So in each case, you can see that the molecular formula is either equal to the empirical formula or is larger than the empirical formula and is a whole number multiple of the empirical formula. For a crystalline compound, we use the empirical formula to indicate the smallest whole number ratio of the atoms or ions present in the compound. Sometimes that's referred to as the formula unit. So for crystalline compounds, we always give the empirical formula as its formula because it really doesn't make sense to write anything else. Another thing that is important to recognize is that some crystalline compounds will have what we call waters of hydration trapped in them. That is, there are spaces in the crystal, and when it crystallizes out of water, sometimes water gets stuck in those spaces and can't be removed. So these kinds of compounds are referred to as hydrates. And how we indicate how much water is trapped in a hydrate is we write the empirical formula or the formula unit for our ionic compound, for our crystalline compound. Then we put a dot and the number of water molecules that are found for every unit of the compound. We're going to do a whole lab on the formulas of hydrates, so you'll become familiar with this. Sometimes people ask, how do we decide on the order of atoms in chemical formulas? It's pretty easy. For compounds that are not acids, we always write hydrogen last, but before any elements from either group 6A, which is the oxygen family, or 7A, which are the halogens or the fluorine family. So H2O, hydrogen comes first because oxygen is in group 6A. HCl, hydrogen comes first because chlorine is in group 7A. But CH4 is the correct order because carbon is in group 4A and hydrogen comes last, except for it comes before elements from group 6A or group 7A. Now, we say that this is for non-acids, hydrogen is written last. For acids, hydrogen is always written first, and we'll do a whole section on acids later on that will help clarify that. For elements that are not hydrogen, we write them from lowest group number to highest group number. If two elements happen to be in the same group, we write the one with the highest period number first. So a good example of this is SO3. Sulfur and oxygen are both in group 6A, but sulfur is below oxygen in period 3, oxygen's in period 2, so sulfur comes first, followed by the oxygen. In NO2, we write nitrogen first because nitrogen's in group 5A and oxygen's in group 6A. BF3, boron is in group 3A, fluorine is in group 7A, so 3 comes before 7. So it's pretty easy. So here are some questions from the OpenStax book. In this case, we're asked to write the molecular and empirical formulas of the following compounds, and we can see that they are all molecules. So carbon is in group 4A, oxygen is in group 6A, so carbon's got to come first. So the formula here for the molecule is CO2, and that cannot be simplified, so that is also the empirical formula. Okay, in B we've got hydrogen here. We know that hydrogen always comes last, but it becomes before elements in group 6A and 7A. Carbon is in group 4A, so that rule about 6A and 7A doesn't apply. So carbon comes first, C2, and then hydrogen comes next, H2. So that's the molecular formula, and that one can be simplified to CH by dividing through by the common factor of 2. Okay, again we have carbon and hydrogen, so we know that carbon is going to come first because it's in group 4A, and then hydrogen always comes last, so we're going to have 4 hydrogens at the end there. This can be simplified by dividing through by the common factor of 2, so the empirical formula will be CH2. Okay, so in our last case here, we've got hydrogen, oxygen, and sulfur. Oxygen and sulfur are both in 6A, but sulfur is in 6A period 3, oxygen is in 6A period 2, so sulfur is going to come first. Hydrogen always comes before elements that are in group 6A or 7A, so our hydrogen is going to come first. So this is going to be H2, SO4 for the molecular formula, and there's no common factor there, so that will also be the empirical formula. Okay, And it looks like we got all of those correct according to the answer key. So this question says, determine the empirical formulas for the following compounds. So we're just looking for a common factor here, the largest common factor, and then dividing through if we can. So it looks like in the first case, we could divide everything by 2 there, which would give us C4H5N2O as the empirical formula of caffeine. For sucrose, it looks like there's no common factor there. We've got 2 even numbers and 1 odd number. So the empirical formula is going to be the same as the molecular formula because we can't simplify. In C, hydrogen peroxide, we've seen this a couple of times. We can divide through by the common factor of 2. So there we are. In D, glucose, important for our metabolism. And it looks like here we can divide through by the common factor of 6. So CH2O. And then ascorbic acid, also known as vitamin C, looks like the common factor here is going to be 2. So C3H4O3. Okay, so I can't see where we can divide through any more, so they all look pretty good. You can check those against the answer key, and everything looks as expected. Okay, so that concludes the section on writing chemical formulas correctly. I hope you found it helpful.